So consider the rod, and if you consider a little section of the rod that has a big mass hanging on it. Initially we have some length of it that we're told is 2 meters, and we're hanging this mass on it, and the mass is 550 kilograms. So because of this weight that's hanging on the rod is going to elongate, and I'm going to exaggerate the elongation. And if you notice now, we have a new length L, and this new length L is one of the things we're going to try and find in a little bit. But notice that we have a force, which is 550 kilograms times 9.8 meters per second squared. That's the weight of that mass. And that is what's going to cause the stress. So the stress is going to be the force that's acting perpendicularly to the unit of area. The unit of area would be just the area of the surface area of that rod, which we're given. So if we plug these values in, we have 550 kilograms times 9.8 meters per second squared over the cross-sectional area, which is 0.30 times 10 to the minus 4 meters squared. Remember, we have to change this from centimeters to meters, the area. This will give us a tensile stress of 1.8 times 10 to the 8th. This is a Newton per meter squared, which is also known as a Pascal. So you can think of the stress as the amount of pressure that is felt. The strain, which is something else we are asked in this problem, is the change in length over the original length, but it's also equal to the stress over the Young's modulus of the material. So Y is known as the Young's modulus, a value that we would look up in a table, or we can be given that as well. And notice that the stress is F over A, so you can get some connections here that might be useful in future applications and examples. We just found out that the stress is 1.8 times 10 to the 8th Pascal. Young's modulus, if we look it up for steel, is 20 times 10 to the 10th Pascal. So the elongation is, or the strain is, 9.0 times 10 to the minus 4. And now notice that the strain is just a ratio of two quantities that share the same unit. So now the elongation, delta L, we can write as the strain times the original length if we use this first equation, which is going to be 9.0 times 10 to the negative 4th times the original length of 2 meters, which gives us 18 times 10 to the negative 4th meters, which is the same as 1.8 millimeters.